All right, here we go. So today we're going to learn about Newton's second law for rotation. And inherent in that discussion will be a little bit of a conversation about both rotational inertia and torque. All right, your two learning targets are down here. Torque is the angular counterpart to force. It's a vector. We'll use clockwise and counterclockwise to describe the direction. And then the result, which is Newton's second law for rotation, says that the net torque acting on an object, notice it's a vector, is equal to the rotational inertia multiplied by the angular acceleration, also a vector. Okay. And so we'll just learn how to apply that. All right. So I'm going to kind of plow through a lot of this because a lot of this is honors and/or stuff we've learned earlier this year already. So we've learned that the net force acting on an object is equal to the mass of the object times the acceleration is Newton's second law, right? And in honors, I really tried to stress the fact that this, if you want to think of it in terms of cause and effect, is an object's acceleration is caused by a net force acting on an object with some mass m. Okay, and so, you know, recently we've been talking about angular motion. So we talked about torque and we talked about rotational inertia and angular acceleration. And in the same way that linear acceleration is dependent on net force and mass, it turns out the angular acceleration is dependent on net torque and rotational inertia. All right, and so the rotational counterpart to this is net torque equals rotational inertia times angular acceleration. Okay, and again, in the same way that I did with honors, I'd like to just, you know, make the point that in terms of like cause and effect, it's actually the angular acceleration is caused by the net torque acting on an object with some amount of rotational inertia. All right, and then finally, I once again should go back and emphasize the fact that net force and our acceleration are vectors. All right, and so your net force will be in the same direction as your acceleration. Your acceleration is in the same direction as your net force. And then the same is true down here for our net torque and angular acceleration equations. All right, so when you talk about Newton's second law for rotation, there it is. Okay, it's the equation that relates the net torque to the rotational inertia and the acceleration. All right, and then down here we just got a real quick review of rotational inertia, which we just talked about in the last video or two. All right, so I think that's all we need to get to there. I think really it's just going to be about kind of solving some examples. All right, so what do we got on this slide? This slide kind of basically just gives us a quick derivation for why that equation is true, right? So we know net force is mass times acceleration, right? Well, we had previously learned that the net torque acting on an object is equal to, why did I put this T in here now? I think I just meant tangential, tangent to your radius when I wrote this. But anyway, the idea is, you know, your net torque is equal to the magnitude of your force multiplied by the length of your lever arm, right? So we previously would have used D there, and then you need to make sure that your force is perpendicular to your radius. So that's what all this rotten notation means, right? Okay. So force is mass times acceleration, right? So if we remember that tangential acceleration is equal to angular acceleration times radius, then, you know, you can do this little substitution here, and then regroup and get mr squared times alpha, right? And I is the rotational inertia of a particle times alpha, right? So this is just kind of a quick, you know, whatever, just kind of hopefully gives you some sort of justification for the fact that your net torque does in fact equal I alpha. All right. Now the actual derivation of this would be much more complicated. You know, for an object that wasn't just a particle, which is basically what's going on here. Is you're looking for the net torque on a particle, right? Because mr squared is the rotational inertia of a particle. I probably shouldn't have gone down that path there. But I guess I should probably remind you that in order for any of this to work, your angular acceleration has to be measured in radians per second squared. Otherwise, your units will not work out the way that you want them to. If I lost you here, I think probably not that big a deal. I probably should have deleted this whole little chunk anywho. So let's move on. So when we did Newton's laws here in advanced placement physics, a very common tool was I said, oh, we can just solve this by saying net force equals net force, right? And basically what we were doing there was we were saying, okay, well, our net force is equal to the total of our forces, right? So F1 plus F2 plus F3 plus, you know, et cetera. And that's equal to the net force, which according to Newton's second law is mass times acceleration, right? So now we've got the angular counterpart for that. We are going to be solving equations now using the idea net torque equals net torque, which looks like this. Torque number 1 plus torque number 2 plus torque number 3 plus da, 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 add up all your torques. That's got to equal rotational inertia times angular acceleration, okay? And once again, everything here is a vector except for inertia, okay? So this is going to be our jam in terms of problem solving. All right, so let's do an example. All right, so suppose we've got a door or a gate or something as indicated here in our drawing. All right, and so you can see we've got the hinge down here at one end. All right, I've given you the mass of the door. It looks like the total size of the door is 0.80 meters, right? And then you've got this big red force applied to it right here, a distance of 0.6 meters away from the hinge, right? Okay, and so the question wants us to find our angular acceleration, all right? And so we're going to solve it exactly like I just said. We're going to do one of these, net torque equals net torque, all right? So inherent in that calculation back here, all of these torques, well, remember, those are just d1 times f1 times sine of theta 1, right? In other words, you got to calculate your torque using the torque equation we learned previously this year, right? Each torque is produced by a force acting on an object some distance away from our pivot point at some angle to that lever, okay? So here, fortunately, we've only got one force that's going to provide a torque, right? So we've got df sine theta equals I alpha. All right, so let's plug in our numbers. So let's see. So D is this. All right, and our force is 50 newtons. And then remember that the angle there is always the angle between your lever arm and your force vector, which for us is 30 degrees, okay? So the left side of this equation for us is just going to be 0.6. I guess I can put units on here. Most of you don't care, but I'm going to do it. So 0.6 meters, there's my lever arm. My force is 50 newtons times the sine of 30 degrees. That's one side of my equation. Equals, let's see, rotational inertia. Well, this is a door, right? And so if you go back to your rotational inertia sheet, as a top view, we can treat this as a rod pivoted about the end, in which case I is equal to 1/3 mr squared, where r is the total length of the rod. Okay, so for us, that's 1/3. Our mass is 45 kilograms. Now be careful here. R is now the total length of the door, right? It doesn't depend on where the force is. It's the full 0.8 meters. Squared, so there's our I, right? So that, what I just wrote here in blue is I times alpha, and solve it, right? Okay, so the red half of this guy, 0.6 times 50 is 30 times the sine of 30 gives you what, 15, all right? So you're going to get 15 Newton meters as our torque equals the rotational inertia, which I have written on this piece of paper, 9.6 kilogram meters squared times alpha. And then if you divide both sides by alpha, or I'm sorry, you divide both sides by 9.6, you'll discover that your alpha is 1.56, And what happens is everything cancels here except for except for seconds squared. And because this is measured now, so where the radians come from is kind of one of those, if you guys really want to know, I can walk you through the math on it. But like I say, radians is sometimes one of those units that kind of randomly appears and disappears conveniently. Okay? But mathematically, you end up getting 1.56 radians per second squared. Okay? The big thing I want to point out here, and I remember this was an issue in honors, is that the D that you use to calculate your torque and the R that you use to calculate your rotational inertia are not necessarily the same thing. Okay? This D is the distance from your pivot point to your force, whereas R is the actual size of the object as determined by the equation that you've got on your equation sheet there. Okay. All right, so let's do another example. All right, so this time we've got these two disks that are stacked like this. Okay. Okay. And down here in this other drawing, we're given the radius of each of the two disks. All right. You are told that the inner disk is pulled. What would that be? Counterclockwise by a torque produced by this 18 Newton force, okay? And then you've got this other mysterious force pulling the bigger disk, all right? And then you're given the masses of the two disks, and the problem gives us our angular acceleration, okay? And so what we gotta do is we gotta find the missing force, all right? So again, this is gonna be net torque equals net torque, right? So that means the torque produced by force number 1 plus the torque produced by force number 2 is equal to I times alpha. All right. So how do we deal with this? We've got two disks. All right. Well, remember, you can simply add rotational inertias. So what I'm going to do is I'm going to figure out what is the rotational inertia for disk number 1 and what is the rotational inertia for disk number 2. The total of those will give us the I for the whole shape. All right. So remember, I for a disk is 1/3 mr squared. No, it isn't. It's 1/2 mr squared. Sorry. So I for a disk is 1/2 mr squared. So here we go. So I1 is going to give us 1/2 times the mass times the radius squared, and it gives you 0.192 kilogram meters squared. So that's how much rotational inertia the bigger disk has. And then the smaller disk has a rotational inertia of 0.072 kilogram meters squared. So when we add these up, we discover that, let's write this somewhere useful, that our rotational inertia combined, when you add those, is 0.268 kilogram meters squared. So that's the rotational inertia of my stacked disk system. Okay? Now, we also know our angular acceleration. We can only calculate one of the two torques, right? We can calculate torque number 2. So let's take a quick second and do that. So notice here, I didn't say it explicitly here, if we're pulling a disk, each of these forces is meant to be the force applied by a rope. I probably should have labeled them as tension. Okay, and so it turns out an interesting fact is that if you pull a disk with a rope and the rope is like wrapped around the disk like this, it turns out that your force will always be perpendicular to your radius. And if you guys remind me, I can show you a quick demo of that in class to kind of help convince you. But it's basically, if you've got a roll of tape, imagine a roll of tape, the tape coming off. No matter what, your tape is always going to be perpendicular, right? Because if you peel off more tape, well, I guess not, because tape is sticky. Bad example. Spool of ribbon, right? And then, here's your ribbon coming off of the spool. If you unwind it a little bit more so that, you're pulling it this way, it's still going to be perpendicular to your radius, okay? Which means for us that to calculate our torques, it's just force times distance, right? So what I know then is this. Torque number 1 is force number 1 times the distance for force 1, which is just that radius. And torque number 2 is its force, 18 newtons times its distance of 0.3 meters. Those are technically both times sine of 90. All right, and then I also need to verify my sines. All right, and so let's see. Oh shoot, I remember I meant to fix this and I forgot. So let's assume that the disks have an angular acceleration of shoot, I meant to put in clockwise in here. Clockwise. So let's assume that that acceleration is clockwise. All right, so we need to then notice that force number 1 is going to produce counterclockwise torque, right? Whereas force number 2 is going to be counterclockwise torque. Okay? So I think we're good now. I think we can plug torque number 1, torque number 2, I, and alpha all into this equation here, right? Okay, and let's see what we get. So, kind of out of room here, so what do we got? So torque 1 is negative F1 times 0.4 plus torque 2 is 18 times 0.3 equals I, 0.268 times alpha, which we decided was negative 3. I apologize for tacking that sign on there at the end. Okay? All right, so let's see, this is meters, newtons, meters, kilogram, meters squared, and solve for your unknown. All right, so if you algebraify all of this mess, you end up getting that negative F1 times 0.4 equals negative 6.204, which if you then divide, you will discover that force 1 is 15.51 newtons. All right, so yeah, that's kind of the deal with those. All right, it just boils down to that net torque equals net torque idea. All right, so I think that's it for that one. How'd we do on time? Not too shabby.